Okay, so let me say a couple words about the next homework. This is all about relations, the kind of thing that we're talking about now. Consider first the set z cross z, where z is the integers, and we define a relation on S by declaring that Mn is related to AB if M is strictly smaller than A when you compare them in the integers. Or in the case that they're equal, N is less than or equal to B. This is sometimes called, this is an ordering relation where you're putting things in order. This is sometimes called the library. So why is it called that? If you're going to look up somebody's name in the phone book, what do? So you look, right, the first letter of the last name, right? You go that, and then what do? Then you look at the next letter and so forth. That's exactly what this thing is doing. It's the library order in a certain sense. So see if you can understand what we mean by that. A, is this relation reflexive? Tell me why. Is the relation symmetric? Tell me why. And is the relation transitive? For the second problem, we're going to consider the set of all functions from R to R. All functions. This is a humongous collection of things. They don't have to be continuous. They can be any mess that you want. Show that the relation, which I'll call twiddle C, on F by declaring the two functions are related if their difference is continuous. So we'll say that these two are related if their difference is continuous. Show that this is an equivalence relation. Show that twiddle D, where we say that two functions are related if their difference is differentiable, is also an equivalence relation. So we're going to learn some of these words presently, probably today. For the next two questions, let EC be the set of equivalence classes of F under the first relation, and ED the set of equivalence classes under the second. Show that if X is in the equivalence classes of D, then there's a Y in the equivalence classes of C, such that X is contained in Y. And on the other hand, show if Y is in the equivalence class of C, then it is a union of a bunch of equivalence classes from D. So this will make more sense later today. Number 3, consider the set of all real vectors in the plane R squared. So those of you that have had a linear algebra, you can think about this geometrically as well. Let V and W be two vectors. We declare that V and W are related if their size is the same, right? If the length of the vectors is the same. Is this an equivalence relation? And if so, describe the equivalence classes. Number B, we now declare two vectors to be related if there is a non-zero lambda in R such that V is a multiple of W. So we're now saying that two vectors are related if one of them is a multiple of the other, where the multiple is not zero. Is this an equivalence relation on R? And if so, describe the equivalence classes. And in part C, explain what happens in part B if we allow lambda to be any real number, not just non-zero. And finally, for those of you that are, we talked about the clock last time, this is related to this. Let K be a fixed non-negative integer. We define two integers in Z to be related. N is related to N modulo K if their difference is divisible by K. Show that this defines an equivalence relation, and show that the number of equivalence classes is given by K, if K is greater than or equal to 1, or infinitely many, K is zero. Okay, any questions on that? All right, so that's your next homework. Start thinking about this, and let's move on. Okay, so the last time we were talking about this business with relations here. So we introduced these this notion of So this is last time. This is 3-1, 3-2-1. We're going to let A be a set in our relation on the set. Say relation R is 1. Reflexive if A related to A for all A. So it's reflexive if everything is related to itself. It's symmetric if A is related to B, implies that B is related to A. And 3, transitive if A is related to B and B related to C, implies A is related to C. And if you have all 3 of them in tandem, it's what we call an equivalence relation. This mimics equality. We had some examples last time where we had some things that satisfied all 3 of these that weren't just ordinary equality. So here's some more examples. This is going to be good for us. Example 3-2-2. Let A be a set and PA is power set. I will call that this is the set of all subsets of A, right? If X and Y are in power set of A, translation, X and Y are subsets of A, we are going to declare that X is related to Y X is a subset of Y. So this is a relation I'm going to put on the power set of a set. I'm going to take all subsets, right? So I might consider everybody in this room. The power set is a subset, right? You're a subset by yourself. You two are a subset. You two are not related because you're not contained in here, and this set is not contained, right? On the other hand, I can take this set, these two, and the set of you first 5 up here, and you are related to you, to the whole set because you're contained in it. That's the way this rule works. Now, is this relation reflexive? Yeah. Yes, because anything is contained in itself, right? Gotcha. Is it symmetric? No. In fact, the example I just gave, the first 2 rows, you 5 and just you 2, you are related to the whole set because you're contained in there, but the whole set is not related to you because you all are too small by yourself to contain everything, right? Is it transitive? It actually is, because if you have a set that's contained, if X is contained in Y and Y is contained in Z, isn't X contained in Z? So this one is actually reflexive and transitive. But it's not symmetric. Okay, let me give it a couple of other ones here. Let me make this remark. How many of you are football fans, sports fans, right? You don't have to admit you're not here, that's fine. But the stadium fills up. Do you know why football is exciting? Among other reasons, I will tell you why football is exciting, because it fails to be transitive, right? You've all seen this, right? If team A beats team B and team B beats team C, are we guaranteed that team A is going to beat team C? Right, football would be boring if that were true, right? But the fact that it's not transitive, makes it exciting. Here's another example of something that's not transitive. How many of you have ever, made a decision with a friend by playing rock, paper, scissors? Right? Everybody knows how to play rock, paper, scissors? That's not transitive, right? Because it would be a boring game if rock beat everything, right? I mean, everybody would always pick rock. Okay, here is another example. Here's kind of a numerical example. Well, let me write down a couple of relations here. A is just some set of four things in it, A, B, C, D. I'm going to have two relations here. R1 is AB, BC, and AC. And we'll have another relation here. AA, AB. Actually, we have ACBC. Okay, what properties do these have? Is R1 reflexive? No, because for it to be reflexive, I would have to have, well, in fact, I would need AA, BB, CC, and DD to be in here, right? In fact, for this to be a reflexive on A, I would have to have all four pairs, AA, BB, CC, DD, right? So none of these are reflexive, right? Everybody okay with that? How about symmetric? None of these are symmetric either, right? This one has an AB but no BA. This one has AB but no BA. And this one has AC but no CA. Everybody agree with that? How about transitive? AB, BC, so I've got AC. This one's actually transitive. How about this one? AA, AB, and I've got AB. This one's transitive as well. How about this one? This one's transitive vacuous, right? I mean, there's nothing to connect, right? So this one's sort of automatically transitive. Any questions? Yes.
Definition of transitive, you require it to be true for.
Right, it's for whenever this happens, then this has to be solved, right?
How does, our, like, if there's nothing.
Well, there is no AB to connect you here, right? And there's no CA to connect you here. So there's no connectors here. So it's sort of like this is false, right? So the implication error is true.
Oh.
Okay, so let me make sure that we, just for your notes, please here. You follow the definition. A relation R on set A is an equivalence relation here, it is reflexive, symmetric, intrinsic. By the way, let me give you kind of a test help out on this. If I asked you on the next test, what is an equivalence relation? You should write this down. But you know what, if you've got extra time to do it, maybe you come back and when you're cleaning things up, tell me what all these mean. Flexible, right? A is AR. ARA is in there. ARA, ARB implies BRA and the transfer problem. You've got time to do it. So, like I said, equals satisfies this. So an equivalence relation is something that approximates the notion of equality. Say, okay, let me acknowledge to you all that I realize that there's more than two eye colors, but I'm going to group everybody in two eyes. We'll say brown eyes and we'll say not brown, which I will call blue, green, violet, if you're Elizabeth Taylor, whatever. So let me ask you this. All people on earth, we're going to assume that there's only two eye colors, brown and blue, in general terms. Is this an equivalence relation? Right, this is a way to relate to people on planet Earth, in the set of all people on planet Earth. Well, let's see. Is it reflexive? Yes, that's right, because everybody has his own, his or her own eye color, right? So everybody's related to themselves. How about symmetric? If you and I have the same eye color, then I and you have the same eye color, right? So it's symmetric. How about transitive? If I have the same eye color as person B and person B has the same eye color as person C, then now notice this is an equivalence relation. But it's not equality, right? What color? You okay? So you were in my equivalence class, right? But we're not the same person. It's not an equality. We're just lumped into the same equivalence class of blue-eyed people, right? Okay, how about this one? And this is going to get me in trouble. We will say that two people are equivalent if they are blood relations. And I know that that's really fast and loose, especially in the South. Blood relations are. But so I am related to somebody. So is this an equivalence relation? Well, I suspect that I'm blood relations with myself, right? If you and I are blood relations, then I and you are blood relations for sure. Is this one transitive? No, can you tell me why blood relations might not be transitive?
They're blood relations with my parents, but they're not blood relations.
Yeah, actually, that's probably the shortest, most efficient ideal. That's right. So I am related to my mother, I am related to my father, and I hope that they're not related, but I'll explain why. So that's right, that's right. A lot of people have cousins, and the cousins of your cousins are not necessarily related to you, right? So this one, the blood relations thing is not, transit. Here's an example. I'm gonna go through this carefully. I've mentioned this before. But let's take a mappy one. Example, and this example will lead very nicely to our next definition. Okay, I want to consider all the integers, right? And I am going to declare m. So sometimes I'll use this symbol as, instead of using the R, this is kind of a notation that is especially used for equivalence relations. We will say the two integers are related if m minus n is a multiple of 2. Or I'm going to say the two integers are related if their difference is even. Okay, is this an equivalence relation? Number one. Someone solved this problem for me. M minus m is 0, which is 2 times 0, which even so. So it's flexible, right? Let's suppose number 2. What does this mean? Minus n is 2k. Everybody agree with that? It's multiple of 2. Well, doesn't this mean that n minus m is 2 times that negative of that k, right? Which is even. So this means that n is related to m. So it's symmetric. Everybody okay so far? One last thing to overcome, this needs to be transitive for it to be an equivalence relation. Well, 3, suppose that m is related to n and n is related to k. So m minus n is 2a and n minus k is 2b for some a, b integers. Anybody know how we can move forward from this? Because where I'm going, well, where am I going? What do I need to show here? I want to show that this is transitive. Right, m is related to k, so any ideas on how I can take my 2 factoids here and move forward? Let's try that. Notice, conveniently, the n's drop out, don't they? Right, so this is m minus k is 2 times a plus b. So m, k. But I'm not quite done with this. I have declared on the set of all integers that two integers are related. Now I can say they're equivalent, because I know this is an equivalence relation. If their difference is even. So, check this out. I don't have much trouble writing all the integers, but maybe we can see a pattern here. What? Give me an integer that's related to one under this, besides one. I already know one's related to this cell. 3. Are there any others related to one? Okay. Oh, there you go. So you can fit over the edge. Would everybody agree that all the odd numbers are related to one? Well, that takes care, and only the odd integer, right? Well, this leaves me with infinitely many. So here's another one. 0. Can somebody name something besides 0 that's related to 0? Now, you're not fooling around anymore, right? All the evens are related to 0. Right? Now, there's something I would like you to notice about this. We have an equivalence relation. I declared the two integers are equivalent if their difference was even. I discovered this is an equivalence relation, and then I noticed that I took the element 1, and essentially half the stuff in here is related to 1, right? And the other half is related to 0, right? Notice that everything is either related to 1 or related to 0, and there's nothing that's related to both 1 and 0, right? This takes the integers and breaks them up into two nice, easy pieces. Actually, this is what equivalence relations do. They take the set, in this case, the integers, and they break them up into pieces. Those pieces, when you put them back together, make the whole set, all the integers. And there's no overlap between the set. There's no integer that's both even and odd. There's no overlap. So this is a nice segue into our definition. 328. Let R be an equivalence relation on the set A. Equivalence relations are so important that they get multiple notations. So I'm going to teach you the language here. Let R be an equivalence relation on the set A. Sometimes I will call R when it's an equivalence relation, that little funny tilde sign. If X is in A, any element that you want, then the equivalence class of X determined by R determined by the relation is sometimes it's written this way: X slash R or X slash tilde. And really, what is this? This is just the family of X. So what the equivalence class of any element is it's just all the stuff in the set that's equivalent to it under the relation, right? It's everything that's equivalent to it. So, for example, the evens, oh, and sometimes I'll write this way. X in a little square bracket. The evens is the equivalence class of zero. It's everything under the relation that I gave you here that's equivalent to zero. Notice, this is the equivalence class of 2. And it is the equivalence class of 40,320. In fact, what even number I choose to represent it doesn't make any difference. This is just the set of all evens. Right? The odds, by the same token, this is the equivalence class of 1, and it's the equivalence class of J 75309. Because these are both. Right? How many equivalence classes do we have here? How many equivalence classes? 2. And each equivalence class has a lot of things in them, infinitely many, right? So all of this. A slash. Here's a couple of examples that I was thinking about equivalence classes. Let's go back to waves here. Couple of waves. This. Declare card 1 be equivalent to card 2 if C1 and C2 have same suit. So in my collection of 52 cards, I'm gonna declare the 2 cards are equivalent if they have the same suit. Both clubs, both diamonds, whatever, right? Now, is this an equivalence relation? Let's go through it. Is any card equivalent to itself?
Yeah.
Sure, because it has the same suit as itself, right? Okay. If I have 2 cards, A and B, that have the same suit, do B and A have the same suit? Yep. And if A and B have the same suit and B and C have the same suit, then A and C have. So this is an equivalence relation, right? How many equivalence classes are there? Okay, good. If you were colorful and poetic, how might you denote these equivalence classes?
Spades, clovers, hearts, diamonds.
Clover's very poetic. That's right. There's an equivalence class for every suit: hearts, clubs, spades, diamonds. Right. Right. So, what is the equivalence class of the queen of spades? All spades. The equivalence class of the jack of diamonds? All the diamonds. Right. So there are 4 equivalence classes. Good. And how many elements in each equivalence class? 13. We declare 2 cards, declare C1, C2, if C1 and C2 have same rank So by same rank, I mean the number on the card, right? So two jacks are equivalent, two tens are equivalent, but a seven and a queen are not equivalent. Is this an equivalence relation?
Yeah.
Well, any card has its own rank, right? If I have two sevens, I've still got two sevens, right? And if card A and card B have the same rank, B and C have the same rank, then A and C have the same. So this is an equivalence relation. How many equivalence classes now? Good. What is the equivalence class of the two of spades?
Father twos, all the twos.
All the twos, two of spades, hearts, clubs, and diamonds. The deck of cards is kind of good. Notice in this case, there's 13 equivalence classes and they each have 4 elements in it. Now, this is when equivalence classes are working very well. Notice in all my examples so far, the equivalence classes are kind of evenly distributed, right? Here, when I said they're equivalent by suit, I had 4 equivalence classes, each with 13 in them. Here I had 13 equivalence classes, each with 4 in them. And even here, I had 2 equivalence classes, but there's a certain amount of symmetry, even though there's infinitely many in both of them, sort of every one. Do all equivalence classes have to have the same elements in them? In these nice examples, there's a nice symmetry. Yes, but in general, no. And we'll see why that's true. So, right. In fact, any question for us? Moving on. Yes.
How do we get, like, those numbers are related to one or zero from the fact, like, from the previous example, which is like n minus 10? Like,
Yeah, that's exactly right. It's the n minus n, right? So if I walk up to you on the street and give you any number, 17, it has to be related to either 1 or 2, right? Because 17 minus 1 is even, or 17 minus 0 is even. In this case, 17 is related to 1.
Okay.
Okay. This is actually one of the biggest deals here about equivalent relations. What is word partition mean to you? Right, it's dividing it. I remember when I was in 4th grade, we were all little troubled children, and they used to partition the class off, right, to make the class smaller. They had this kind of divider. What they took all the 4th graders that were raising Cain, and they put the partition across, and it broke us into 2 smaller 4th grade classes that were more controllable. What a partition is, when I think of partition, I think of maybe a pie. This is a good picture. What do? You take a pie and cut it up into a number of slices, right? If you put all the slices together, you get the whole pie, right? So the pie is the union of all the little pieces of pie, right? And there's no overlap between the pieces of pie, right? I don't accidentally eat my piece of pie and I'm eating a piece of yours. It's broken up into separate pieces, right? So let me give you something formal. Definition 331. Here we're going to let A non-empty set. Set. I'll ask you about that in a moment. We say that fancy P is a partition of A. If, so what is fancy P? it's a collection of subsets of A, not the power set, just some collection of subsets. If P is a collection of subsets of A, that satisfy number one, if X is in P, now remember what this means is X is a subset of A. And X is not in. I don't want any empty sets in. Two, if X, Y, if I have two elements of the partition, then if I walk up to you on the street and give you two elements in the partition, they're either exactly the same or there's no overlap. The intersection is empty. And number three, the union over all the sets in the partition is all right. And this is why a partition is exactly how I described it. What a partition is think about how many of you are puzzle enthusiasts, jigsaw puzzle. Anybody work those? Yeah, so you've got all those puzzle pieces. This is what a partition is. It's a jigsaw puzzle pieces. Here are the rules. No empty pieces, right? I've got to have something, right? If I have two pieces, those two pieces are either the same or there's no overlap, right? If you've got jigsaw puzzles that are overlapped, you need to get a knife and cut them apart. Right? That's a problem, right? And if you put all the puzzles together, the union of all the pieces of the puzzle, you get the entire set, your finished puzzle. This is an example of a partition. Notice the way that this is drawn. Notice I have, in this case, 8 puzzle pieces, right? Would everybody agree that none of these are empty, right? No two different ones overlap, right? And if I put all the pieces together, I get my big rectangle. That's all a partition is it's taking a set and it's splitting it up into disjoint pieces that when you take all the pieces and put them together, you get the whole thing. So here's a couple of examples. Actually, I think this is like a proposition there. So three. Let A be a non-empty set. By the way, I want to be talking about a non-empty set here because you're not going to be able to put together the empty set with pieces of the puzzle that aren't empty, right? So we throw out the empty set because it's a bit silly. There are always two ways to partition. In fact, there's usually many more. Did anybody think what they are?
One way would be to as have just one, for example, and another would be to let each element its own partition.
Right. This is the jigsaw puzzle that even Jim can solve. You can partition the set just by taking the whole set, right? Very disappointing. You open the box and it's just a solid picture, right? Not too challenging to solve, right? But you could certainly do this, right? This is a non-empty subset because we're assuming that A is not empty. And this holds vacuously, right? And so does this. And what was the other one?
If you just put each element of the set its own.
The partition take all the elements of the set A and make each element its own puzzle piece. That's probably the hardest jigsaw puzzle, right? But you can certainly do that, right? Because notice this is not empty because X is not empty. And notice if little x and little y are not equal, then they can't overlap because they're different elements by the fact that they're not equal. Everybody agree with that? And if you take the union of all these sets here, you're going through every element in A, so you get all of A. Everybody agree with that? By the way, I said that there's two ways, and there I've listed them. I did not say that there's two distinct ways. Can anybody give an example of a set that there's only one way to partition it? A set with a single element. And if you have a set with only one element in it, these two are exactly the same, right? And there's only one way to do it because there's only one non-empty subset of a set with one element. Notice if you have a set with two or more elements, you always have, well, at least four subsets in the power set. So there should be more interesting ways to put those together. Okay. Any questions? Okay, I'm gonna give you all a last theory. Yes,
Is there a useful property that X equals Y gives us, or do,
what's this now? So
like, why, is there anything, is there any useful property that gives us? I feel like we just have the second part.
what this, all this means is my set's in the partition after disjoint, right? So if I pick two elements in the partition, I might have accidentally picked the same one twice, right? And that's what covers this. This basically just means, but yes, it is useful in the sense that, well, one of the big things we get, and this is an important thing. So this is a big takeaway, and this theorem is sort of the lead into it. The big takeaway is this. If I give you an equivalence relation on a set, it partitions the set. That equivalence relation determines the partition. You've seen that in every example that we've done, right? The equivalence relation where I said the two cards are equal if they have the same suit, that partitions that set of cards into hearts, clubs, spades, and diamonds, right? When I said two integers are equivalent if their difference is even, that partitions the integers into even and odd. So here's the last theorem. And it turns out that if I have an equivalence relation, I get a partition. And if you walk up to me on the street, give me a partition, it gives you an equivalence relation. They're actually sort of the same notion. So I will give you this. That'll be it for the day. Let A be a non-empty set and R an equivalence relation. Set. And R an equivalence relation. Number one, for all X and A, for all X and A, the equivalence class of X is contained in A. And X is in. So no equivalence class is empty. two. The union. X and A of the equivalence classes of X is all A. And three. X is related to Y or is equivalent to Y if and only if the equivalence class of X is equal to the equivalence class of Y. So this actually means that equivalence relations form partitions, and we'll get deeper into those weeds on Monday. Any questions? Questions? Well, I encourage y'all to check out the Math Club. Other than that, y'all have a good weekend, and we will see you on Monday.